Hi everyone, this is Dr. Justin Essery from Rice University. This is a makeup lecture for POLI 395. I'm going to make up a little bit of the descriptive statistics and graphs section that we weren't able to get to on Thursday's class, Thursday the 18th, because we just ran out of time. Then I'm going to make up the material that was originally scheduled for Thursday the 18th that we weren't able to cover due to a snow day, which is about the application of scientific methods to the social sciences and sort of an introduction of basic concepts of science. So let's spend a few minutes finishing up some basic materials on descriptive statistics and graphs, and then we'll move on to discussing science. So last time at the very end of class, we were talking about box and whisker plots and histograms, some basic plotting tools and statistics. And you can see here I have my week1.r file open from the class RStudio server. I'm in my home directory right now, but you might want to change your directory to POLI 395 in order to be able to access that file and the other data files that we're going to be working with. You may also want to make sure to set your working directory, as we've done in the past, to POLI 395 to make sure that you're able to access files from the R console that are in that folder. As we've discussed previously, that's pretty much something you should do at the beginning of every class, including the ones that happen on the web. But what I want to talk about now is an interesting example of using some of these methods to address a question which may be of social, scientific, and maybe even personal interest to you. An interesting source of data to analyze and an interesting sort of thing in general, I think, just as a social science application, is the existence of these prediction markets. Prediction markets are a way of forecasting the probability of certain events. And the way they work is you ask people to bet actual money, real money, on propositions by buying securities. It is similar in a certain sense to betting like in Las Vegas or something, except that you, instead of sort of booking your bet with a bookie or with a sort of a centralized casino or gambling house, what you do is you buy a security on the market that has a certain value if something happens and a different value if something else happens. So let me give you an example. Well, actually, so if the proposition that your security, your particular sort of bet pays off, you get, let's say, $1. It's not always $1, but often it's $1. And if you're wrong, the security is worth $0. So it's a little bit like buying shares, where the value of the share depends on something happening in the real world. So the price of in this sort of scenario, you can buy and sell these shares. You can buy as many as you want. There's typically a sort of a fixed market for these shares that are out there. I suppose I think the quantity demanded is actually, in other words, there's not a fixed supply, I think. I'm not sure. Now that I think about it, I'm not sure how the supply of these securities is determined, if it's infinite or not. But the way this works is there's a certain amount of securities that are floating around in the market, and people can buy and sell them at will. So if I buy, let's say, 1,000 shares of President Trump will not be impeached, okay? Or actually, it might be easier to talk about the positive end. So 1,000 shares of President Trump will be impeached before a certain time. Let's say before the next inauguration, before January 20th or whatever, 2020 or 21. If he actually is impeached and I own 1,000 shares that say President Trump will be impeached, then I get $1,000. If he's not impeached, I get nothing. They're worthless. And so what that means is when I buy this share, I am essentially making the calculation that, well, whatever the price I paid for these shares is, it's still worth it to me to buy them because I think I'm going to get the $1,000, right? I think I'm going to get the payoff from this share. So if I buy 1,000 shares of President Trump will be impeached, let's say for 50 cents a share, right? So I pay $500 for those shares. what's happening is I'm saying I think that my expected payoff is more than $500. In other words, I think there's more than a 50% chance that he's going to be impeached. If I decide not to buy them, if I say I'm not buying the 50 or 1,000 shares of that for $500, what I'm saying is it's probably worth less than $500. There's probably less than a 50% chance that he's going to be impeached. And what you do is you just get a whole bunch of people buying and selling these shares, just like I just described, and via market mechanisms, which you may have learned about in your Principles of Micro class, Principles of Microeconomics. An equilibrium price emerges in this market, and that price is forecast by the market as the probability of the event occurring. So to continue our previous example, if we're buying and selling shares about President Trump being impeached, let's say the price of those shares equilibrates to 38 cents per share. What that means is the market has decided that there's about a 38% chance of President Trump being impeached. And the reason this works is if a lot of people thought there was more than a 38% chance of him being impeached, they'd buy the shares and the price would rise by the laws of supply and demand. When the demand for the good goes up, the price goes up. So therefore, by the market's judgment, if the price is 38 cents a share, well, the probability of being impeached has to be around 38%, because if it was higher, people would buy, and if it was lower, people would sell. That's the sort of basic logic of how these prediction markets work. They depend on a certain wisdom of the crowd. They depend on sort of lots of buying and selling by lots of different people with lots of different access to information. And they rely on markets essentially being efficient information mechanisms, right? They rely on the price clearing or the quantity clearing aspect of the market being linked to sort of information and judgment possessed by buyers and sellers in the market. So let me give you an example of something that was recently on the market, and then actually, the event was decided. This is from the Predicted Markets. The proposition was, will then President Obama pardon Chelsea Manning or commute her sentence? So that was the proposition. I buy a share. If the sentence is commuted or Chelsea Manning is pardoned, I get $1. If not, I get nothing. So I think this quote was from January 20th at 11:59 p.m. The price was 37 cents, which means that the market at that time thought there was a 37% chance that Chelsea Manning would either be pardoned or have her sentence commuted by President Obama, right? So, and you can see how that judgment of the markets changed over time. It was around zero, and then suddenly it spiked to almost 50 cents, actually a little over 50 cents, when essentially information started to filter out that President Obama might be considering this. There is a logic to why we might want to use a mechanism like this to do an assessment, and the logic is, well, when you ask people, sort of, there are lots of ways of forecasting how people will decide. You could just ask them, right? You could do a polling mechanism. So one thing that prediction markets have also done in the past and probably will be in the future is predicting who will win the presidential election, right? And you can do that with a prediction market. You can say, $1, I'll buy shares of Hillary Clinton wins the election, right? It pays $1 if she does, $1 and $0 if she doesn't. There are lots of ways of answering that question. You could answer it with a poll, right? You could just take a poll of American voters and assess how many people are going to vote for so-and-so, how many people are going to vote for so-and-so. But maybe we believe that prediction markets are better than simple polling. Prediction markets, first of all, require you to put real money on the line. So you have to really believe in some sense that you're right. And you have to have some, hopefully, if you're a rational person, some basis for believing you're right, not just wishful thinking. And so prediction markets sort of put skin in the game for the people making the predictions. Secondly, polls can be wrong in innumerable ways. Your sampling frame is off. You don't poll enough. You poll the wrong people or whatever. You have your weighting matrix is messed up. All kinds of reasons that polls can be wrong. Polls basically rely on generalizing the individual preferences of people to the group, right? He's using a bunch of individual measures you've gotten and then using that to create an aggregate group measure, right? How many people are going to vote for a particular candidate. The prediction markets don't work on that principle. The principle for the prediction markets work on the principle of what do people think is going to happen, and presumably they have some reason for thinking it's going to happen that way. They may be reading polls and building that information into their judgment process, but they may be reading news stories, they may be looking at other indicators as well, and they may be aggregating that information in a different way. And so, maybe polls are not really the best way to figure something out. Maybe it would be better to use these markets and hopefully make use of the greater incentives they provide and the greater range of information they provide to make this judgment. Now, I think both polls and prediction markets have their ups and downs. I don't think markets are necessarily always perfectly rational. For example, there are bubbles that exist. They've existed in the past. Some might argue, including me, I think. There is a bubble on Bitcoin prices right now that has reached its height and is now sort of crashing back down to reality. Obviously, I could be wrong about that, but we have seen bubbles like that in the past. So, markets don't always make perfect decisions. But they have different strengths and weaknesses than polling. And, I don't think I'm ready to say they're better than polling, but I am ready to say they make use of different information than polling, and they may give us, in combination with polling, some additional insight into the process. So what we're going to do now is we are going to look at the actual data from the Chelsea Manning prediction market. And in this case, we actually have the advantage of knowing what happened, right? So we're going to look at this data, analyze what the markets thought was going to happen, and then we can sort of compare that to our current view of what actually happened. Then we'll look at a similar proposition bet regarding Edward Snowden. Who was also the subject of speculation of maybe he would receive some sort of reprieve from President Obama. We'll look at that prediction market data, and then we'll look at what happened there. So let's get ready to analyze this data. All right, so what we're going to do is we are going to make a little line plot of the Chelsea Manning prediction market data that I obtained. And we're going to just plot that to look at the market's changing judgment of the proposition that Manning would be either pardoned or have her sentence commuted by President Obama. So I've sort of, in the slideshow here, I've laid out a bunch of commands that might be useful for this. I'm going to clear out the existing information or data. I'm going to read in, so this is a data set, a different data set containing prediction market data related to Chelsea Manning. I'm going to load a library. I'm going to load the LubraDate library, which is just helpful for dealing with some date information that is present in this data set, because obviously there's a closing price on every single day, which means there's a lot of different dates in this data. I'm going to convert using the LubraDate library. The text, literally there's a text field that shows you sort of what the date is. I'm going to convert that to a date object. And then I'm going to use the plot command, which we've already studied in R, to plot this data, a line plot over time. So those are the basic commands I'm going to use. These are all, I should also note, already available in the week1.r file that's available on your RStudio server. So you should be able to literally just run these commands along with me. So if I just run these commands, I'll sort of show you the answer first, and then we'll talk about what's going on here. And there we go. So let's see. Might be better if I squish this down a little bit. All right. Okay. So what do I have here? What I have here is a plot. On the y-axis, the closing share price for a share of Manning will be have her sentence commuted or be pardoned. And on the x-axis, I have the date. So this is the closing price on each date. So if you can see I actually read in some data, this CSV file that contains the relevant data here. And it might behoove us to actually take a look at what this data looks like. So if I type head manning.data, I'll get a little sort of, this is what's in the data set, right? I've got a date string. You can see it's called date string. That means it's a text string. It's basically letters, or R sees it as letters. R doesn't know how to put letters like strings. It's not going to order them in a reasonable way in this case. So the first thing we're going to have to do is convert that to a proper date so that it knows to put the dates in order when we plot them. And then I've got a bunch of different sort of variables here. And the one I'm most interested in is the closing share price, right? That was the price of a Manning share at the end of the day, right? So I'm just sort of comparing end day prices for each date. And you can see here there's other stuff like open share price and trade volume. You can also see there's this new date variable. Well, I created that, right? So I made that using this LubrDate library. And the reason I made this, you can see I'm adding a variable to the Manning.data dataset. It's called date. That's separated with a $sign. And I'm storing that object, this date function, which is just loading in the string. If you look at what the date function does, whoops, date. It's in the LubrDate library. So if I click on this one, that's what I'm using. I'm in the LubrDate sort of package. I had to load that library in order to use this function. And what it does is I feed in essentially information, a date time object, right? And it spits out a proper sort of variable type that R can understand. It spits out a date. So if I compare, for example, let's see. That's what R is seeing in the date string. You can see it's actually technically treating as a factor variable, which the distinction between factors and strings is R does recognize a factor as sort of having levels, but it's not necessarily going to put them in any kind of reasonable order. If I instead look at date, right, which is created by this date function that I fed in, now you can see it's organizing these things into sort of labels that make sense and have a common date format. It's not, in other words, it knows to put them in order and it knows their dates. Let's see. You can see date time must be A, and then there are all these different possible formats. This format, 2016-1216, is a standard format, right? It's a standard format for how dates can be read in. Therefore, we're able to just feed it right in and change it to a date. And then this final thing plots the line. Now you'll notice I'm doing close share price versus date, and I've added a new command, or a new argument rather, that we haven't necessarily seen before. Type equals L. So if I don't put in type equals L, if I do this, it's going to plot it as points. And I want to make sure that for readability purposes, I put it in a line. So I just specify type equals L and it gets a line. And if I want to prettify this, if I want to add a main title, I want to label the date, maybe I want to change the color of the line to red, I want to label the y-axis, I want to maybe change this is y-lim here, this is the dimension, or the range of the y-axis. I can do that as well, and I get a slightly prettier looking graph. Now you can see my main, because this window is relatively small, my label is running off the edge. If we were to blow this up, so for example, if I were to expand this window like that, it would look better, right? So this is partly, the fact that the label runs off the screen is just an artifact of I'm doing this on a relatively small screen, but that looks pretty nice. And so what do we learn from this, looking at it? Well, we learned that until basically January 11th, right? Something must have happened on January 11th. The market was thinking there was about a 10% chance that this was going to happen. And then suddenly on that date, that expectation spiked. Some information came into the market, and that information spiked, and the prediction spiked to over 50%, and then sort of settled down to around 45%. So the market learned something on this date, and then suddenly the forecast went way, way up. And in fact, if you excuse me, if you look at what actually happened, we know that Chelsea Manning was pardoned. I'm sorry, had her sentence commuted. She was not pardoned, but she had her sentence commuted by President Obama, and now she's running for Senate in Maryland as of this recording. So the market was sort of, I don't know. It depends on how you want to classify being right, right? Saying so there's a 45% chance of something happening doesn't mean you're saying there's a 100% chance of something happening. So whether it's right or not, I suppose, depends on whether we reran history 100 times, and in 45 of those times she had her sentence commuted. But nevertheless, the market was correct in sort of guessing that the probability of this went way up, and in fact, it did actually happen. We could also do the same thing for Snowden predictions, right? So it's exactly the same process, but we're using data about whether Edward Snowden would have some sort of pardon, be pardoned by President Obama. And in fact, what I'm going to do is I'm just going to take the existing plot here, and I'm going to add, let's see. I'm going to extend this down. Yeah. I'm going to add the Snowden data to this. I should say that this label is slightly misleading. I should say pardon or commutation. That's really a more accurate depiction of what's happening here. You can't even see it now. But anyway, that's more accurate. So this is data from a prediction market trying to predict the possibility that Edward Snowden gets a pardon from President Obama. So I read in this data just like I did last time. I have to convert the date just like I did before. And I'm going to add, using the lines command, I'm going to add a Snowden pardon line to this data for the same dates. And what you can see is the markets did not think that Edward Snowden was going to get a pardon. It never learned anything that changed from President Obama. It never learned anything that changed that expectation. And in fact, that didn't happen. Edward Snowden did not get a pardon. He's still in Russia, I think. So last thing I'm going to do here is add a little legend to the plot using the legend command. You can learn more about the legend command by typing !legend. There's lots of different subcommands or arguments that it can take. For the purposes of this plot, I want to put it in the top left, so I put a little top left in quotation marks here to say I want the legend at the top left. I have two lines, Manning and Snowden, so I put in a string Manning and a string Snowden. The Manning line is red, the Snowden line is blue, so those are the colors. I put in the color argument. And both are non-dash, just sort of regular lines. So LTY, it says it's short for line type, and both line types are 1. So that draws a little box here that says the red line is for Manning, the blue line is for Snowden, and you can see clearly the market learned something about Manning on that January, whenever that was, and it didn't learn anything about Snowden on that date. So therefore, the prediction markets drastically changed for Manning, and they stayed the same for Snowden. So R can be used to make cool little graphs like this that kind of illustrate an interesting point. Okay, so let's see. Here. So to make sure that you know how to do this, what I would like you to do now, and you can sort of, after the question is asked, you can pause the video and do this, and then we'll come back. There's an S&P 500 data set in the RStudio server in the POL 395 folder. And in fact, if you go down here and you look at files, you should be able to scroll down here and see sp500.csv. That's the S&P 500 data set. And let's see if I go back to, what am I doing here? Oh, yeah. There we go. I'd like you to use the SP500 data set to answer the following question. Assuming we can use the closing share price of the S&P 500 as a proxy for the health of the economy, which that is not the best measure, in my opinion, for the health of the economy, but we're going to accept this measure as being flawed, but still what we have available and perhaps insightful in some way. So we're just going to take that as a valid measure, even though there's some doubts about that. So we're going to use that as a proxy for economic health. And I'd like you to construct a plot that enables you to answer the question, how has the economy done under the first year of Trump's presidency compared to how it did during Obama's second term? And there are three options here. Better, worse, and about the same. And if we were live in class, I'd ask you to hold up your index card to indicate which one you did or which one you believed. But I want you to construct that line plot, pause the video here, construct this line plot, and then we'll construct it together, and you can make sure that you did it right. So I think this would be a good time to pause the video and try to answer this question now. All right, so now that you had a chance to try it on your own, let's do it together. So the first thing I'm going to do is just clear out whatever's in my memory, the Manning data or whatever might still be in there. Excuse me, I'm going to load the SP500 data set. And if I look at what's in this data, you can see I've got just a counter, that's X, a date, and the SP500 closing price for that day. So I have to use lubridate and convert the date to a proper date. So if you actually go here, you'll see the original date is just a factor with a bunch of levels that won't order it properly. But now the converted date is a proper date format. And now I should be able to do a plot. So I should be able to plot, let's see, the variable is called capital SP500. SP500, oops. Against date C for converted. Data equals lowercase SP500. You'll notice it treats lowercase and uppercase differently, as R always does. And I want to do a line plot. Okay. So this is a plot of SP500 closing prices over time. This is the price here. This is the date. And we might want to put in a line, like a vertical line that indicates when President Trump took office, which would have been January 20th, 2017. So we can do a couple of different ways to do that. We might do it this way. We might say, let's see, use the which command. Which will tell you literally which observation meets a certain criteria. And we might say which, let's see, date. We'll use the capital, no, we'll use the lowercase one. Let's see, 2016, no, 2017, January 20th, that might work. Oh, lowercase. Lowercase and uppercase is very important, as I mentioned, and then probably forgot. Aha, it's observation number 1050. So I may be able to do the following. I may be able to say, I'm going to put in a line. It's a vertical line at the point. Well, I might be able to do it this way. Yep, that's not going to work. Okay. So let's see. Let's try this instead. It's number 1050. Let's see if I put in a vertical line at 1050. Yeah, that didn't work either. No. Really want to put in that vertical line. How would I do it? Well, let's see. A little Googling turned up the right answer. I was on the right track, but I need to actually feed it the date object. So I want to put it on a vertical line at as date. You have to convert it to a date, 120. So if I do that, oh, I must have an extra parenthesis in there somewhere. Bam, there is when President Trump took office. And if I want to even get a little fancy, I can redo this plot. And I'll comment that out because I don't need it anymore. Now it's a dashed line. So the question would be, how's the economy doing since President Trump took office? Well, there are actually two ways to look at that. One way to look at that would be, obviously it's doing better, right? You can see the SP500 has gone up substantially since Donald Trump took office. That would be an indication, if we just use that as a measure of economic performance, economy's gotten better. Another way of looking at this is you could look at it as, has the growth rate changed, right? So we're not looking now at the level, we're looking at the trajectory or the derivative in the calculus sense of the word. And so in that sense, if you're looking at it that way, you might say, okay, well, since 2013, it sort of was growing at a certain rate, and then in 2015, it kind of flattened out a little bit, and then it sort of turned up again in about 2016 before the election really started, and it's been growing pretty much the same since 2016. So there are two ways you could sort of look at or interpret this data. You could look at it and say, S&P 500 has grown, obviously the economy's gotten better. You could also look at it and say, well, the growth rate has pretty much stayed the same since 2013 all the way through to the current day. So not much has really changed. So this is kind of an interesting question because it illustrates that you can possibly provide more than one interpretation of an apparently objective plot just by sort of how you interpret it. I think I would tend to favor the growth rate interpretation, meaning the growth in the S&P 500 is really what we care about, and the growth has basically stayed the same. So I'd say the economy is doing about the same as it was before. But if you wanted to say, you know, the S&P 500 is, if you wanted to make the argument, the actual level of the S&P 500 is some measure of the level of wealth or something, you could possibly make the claim that it got better. I tend to favor the growth rate interpretation because I think the growth rate interpretation is consistent with, for example, growth in the economy, right? So how's the economy growing? How are new jobs being created? And the economy is basically growing at the same rate it was before. But I think both interpretations could possibly be argued. Okay, so that's it for sort of finishing up what we were going to do on descriptive statistics. Now I want to transition into talking about science. So for this part of the lecture, at least for most of it, well, actually, I take that back. I was going to say you won't need RStudio, but you will need RStudio for one thing we do. So keep RStudio sort of hot and running. We'll get back to it in a second. But let's transition to talking about science. All right. So now we're going to transition to talking about science and the scientific method. Hopefully, we're going to answer 3 questions. First, what is science? What can it be used for? And perhaps most importantly for our class, how can we apply scientific methods to politics, or can we do it at all? If we can, how do we do it? And if not, why not? So I guess it's actually 5 questions, but that's what we're going to talk about. And I'd like to start with a little video by Richard Feynman. Richard Feynman was a Nobel laureate physicist, very famous for making some discoveries in quantum mechanics. Also famous, perhaps equally famous, for being a teacher of physics and a very colorful personality who said a lot of quotable things. And it turns out he also, in addition to his day job, commented on social science. In this video, he comments on social science. It's been uploaded to YouTube. So I'm going to show you a little bit of that video. This is slightly meta. We're now watching a video on you're watching a video on YouTube that's playing a video on YouTube. So, but nevertheless, I'm going to play that, and we'll watch that for a second, and then we'll come back and discuss it. So here we go.
Because of the success of science, there is a kind of I think a kind of pseudoscience that social science is an example of a science which is not a science. They don't do scientific. They follow the forms. You gather data, you do so and so forth, but they don't get any laws. Haven't found out anything. They haven't gone anywhere yet. Maybe someday they will, but it's not very well developed. But what happens is, at an even more mundane level, we get experts on everything that sound like they're sort of scientific expert. They're not scientific. They sit at a typewriter and they make up something like, food grown with fertilizer that's organic is better for you than food grown with fertilizer that's inorganic. May be true, may not be true, but it hasn't been demonstrated one way or the other. But they'll sit there on the typewriter and make up all this stuff as if it's science, and they become an expert on foods, organic foods, and so on. There's all kinds of myths and pseudoscience all over the place. Now, I might be quite wrong. Maybe they do know all this thing. But I don't think I'm wrong. See, I have the advantage of having found out how hard it is to get to really know something, how careful you have to be about checking the experiments, how easy it is to make mistakes and fool yourself. I know what it means to know something. And therefore, I see how they get their information. And I can't believe that they know it. They haven't done the work necessary, haven't done the checks necessary, haven't done the care necessary. I have a great suspicion that they don't know that this stuff is, don't know, and they're intimidating people. But I think so. I don't know the world very well, but that's what I think.
All right, so as you can probably observe, the video was recorded quite a while ago. We don't type on typewriters for the most part anymore. But what Feynman is sort of arguing is that there's a certain attitude toward knowledge and a certain set of commitments you have to make in order to be an effective science, to be practicing science. And those are important in order for the results that you produce to be scientific. And so what we want to talk about today is what those characteristics are, what those sort of ideas are, and whether it's possible to live up to them in political science. So what is science? Well, sort of at a sort of talking about the consequences, I suppose, rather than the procedure itself. Science is a way, and historically the most successful way, that knowledge about the physical world and the things in it are obtained. Maybe it won't surprise you, maybe it will, but although science has been very successful, there are many debates about what science is, and in fact, practicing scientists, even people who, if you take a group of people, all of whom would agree that all the other people were scientists, in other words, they would all agree that they're scientists, they wouldn't necessarily all agree on what science means, what the important characteristics of science are, what are sort of the sine qua non of scientific work. It's not necessarily a cut and dry topic. It's an active. There's an entire area of research called philosophy of science about trying to figure out what science is and how it works, and to learn more about it. So I'm going to begin with the idea, which I should clarify is not an indubitably true idea, but one idea about science, that science is induction. Induction is the process of drawing conclusions about the present and future via the observations of past events. So a lot of the work we do in all areas of science, including political science, is looking at what happened in the past in order to predict what happened in the future, what will happen in the future, and to understand what happened in the past. So, for example, if we want to do something like predict presidential election outcomes in 2020 or going forward, we might look at what happened in the past, look at what factors seem to be influential in predicting past election outcomes, and then use that information either qualitatively or statistically, quantitatively, to make a prediction about the future and to understand what factors influenced things in the past. That's the basic idea of induction. But induction it can be problematic. And what I want to do is to explain why induction can be problematic is to talk a little about something called the black swan problem. So I'm going to go ahead and close this here. I'm going to close week 1. And I'm going to open in the POLI 395 folder a file I've uploaded called blackswan.r. Nothing to do with the movie about ballet dancing, in case you're wondering. The black swan problem is a little something like this. So suppose, I don't know why you'd want to answer this, but suppose that you wanted to answer the question, do black swans exist in nature? And one way of answering that question would be induction, right? You go out, gather a lot of data, look at a lot of swans in this case from all over the place, and then use the data you've collected to generalize to the larger group of all swans, including the ones you haven't looked at, and maybe even future swans that you couldn't possibly have seen yet because they don't exist yet. And so you collect a lot of data, and then you use that to essentially conclude whether there can be any black swans. And historically, if you were to have done this, Until the discovery of Australia, where black swans do exist, you might have concluded with this procedure that there are no black swans, right? You gather, if you just looked at a bunch of swans from all over the world except Australia, which hadn't been discovered until, I'm not sure, it's the 1700s, I think it was discovered, pretty late. I'm not sure exactly when. 1600s maybe? Yeah, I'm not clear on that. Probably I was much earlier than that now that I'm thinking about, well, anyway. This ain't geography class. Anyway, so if you weren't looking in the right places, essentially, you never would have found the black swans, and you might have concluded there are no black swans because your data set has no black swans in them. So what I've done here is I've created a little R package to simulate a data generating process which can end up being misleading for a slightly different reason. So in the first reason with Australia, it's because you're not looking in the right place. You don't know where to look. Another possibility is that black swans are just rare. They don't happen very often, and even a very large data set may not turn up any examples, right? So what I've done here is this, of course, this first line just erases anything that might be in memory. The second line makes sure that our random number generators and our computers will all produce the same answer. So if you set the random number generator seed to a common value, and then we execute all the same commands in all the same sequence, we should get the same answers, even though we're drawing some random numbers in this simulation, because we've basically pre-initialized the number generator to start at the same place, if that makes sense. So these commands here, lines 3 through 9, are a function. The function is called black swan. And all it does is it draws many samples out of a uniform distribution. So a uniform distribution has just an equal probability of any number between 0 and 1 coming up. And then if the number it comes up is less than 0.99999, so in other words, almost always, the swan that is drawn from this little simulated process will be classified as white. And if the number that we draw, the random number, the uniform random number, is greater than 0.9999, so for example, if we happen to draw the number 0.99991, then the swan will be classified as black. So what this means is there is a 0.99999 probability, or a 99.999% probability of observing a white swan in this little simulation process. And there's a 0.001% chance of observing a black swan. Okay? So the induction, if I run all this code and then I say, all right, I've created a function now. The function takes one argument called n, which is just the number of data samples I wish to draw. Let's say I simulate observing 10,000 swans, okay? Well, if I simulate observing 10,000 swans in this process, what I discover is I observe 10,000 white swans and no black swans, right? So induction would lead me to believe in this case there are no black swans, right? And I might, suppose I collected or I gathered a sample of 100,000 swans. Again, no white swans. I'm sorry, no black swans, rather. Let's say I do 1 million. Finally I observed a small number of black swans, 13 black swans, okay? So my first two induction data collection processes gave me information which would possibly lead me to believe that there's no such thing as a black swan. But of course, I knew that was wrong. I created the data generating process in such a way that I know that there can be a very small probability of a black swan. And as long as I collected a data set of sufficient size, in this case a huge size, a million observations in this case, I'll find a few. But you may have looked at these first two data sets, and if you didn't know any better, you might conclude, oh, well, everything all the data we've collected so far leads us to believe there's no such thing as a black swan. The purpose of this is to demonstrate that induction as a scientific method, which makes a lot of sense, looking at past data to predict the future, or looking at a sample of data to generalize to a larger population, It makes sense, and in fact, it is what we do quite a lot, but it's problematic. It's not a direct line to the truth. The sample you collect may be unrepresentative. So in our little simulated example, even a huge sample might not be huge enough to detect a small portion of the population that you're looking for. Or going back to the historical case of Australia, looking at swans all over the world doesn't help in detecting black swans unless you look in the right place. We didn't even know to look in Australia because we didn't know there was an Australia until we did, and then we knew. That's not the only, those are sort of two problems, but those aren't the only problems. Causal processes don't necessarily stay the same over time. For example, the way that the factors that determined whether a president was likely or unlikely to be elected, let's say in 1800, may or may not be the same processes that determine whether a president is likely to be elected in the year 2020, right? You can think of a lot of reasons why. First of all, the mass media has changed dramatically between 1800 and 2020, right? 2016, 2017. That's a big factor that didn't exist back then, and that may influence how presidents get changed, how presidents get elected, how politics happens. So looking at past data may not be informative if the process that sort of generated that data has changed between then and now, if we're interested in studying now. The bottom line here is the events of the past are not a guarantor of the events of the future, and this is sort of generically stated as the problem of induction. We cannot definitively learn about a natural process or a physical process by simply observing a subset of that process in nature, even a very large subset, because there are many reasons why what we observe may not generalize to the larger process. And in the sort of history of thinking about science, this idea is typically attributed to David Hume, a Scottish philosopher, one of the members of the Scottish Enlightenment. So because of the problem of induction, we can't simply observe what's out there and uncritically draw conclusions about how nature, how physical processes, how politics works. So we have to do something else, and philosophers of science have been working on what we can do to use data productively to come up with a sort of philosophically defensible scientific method. And one idea that's been very influential in the practice of science is falsificationism. Falsificationism was formulated by Karl Popper at the turn of in the early 20th century. And the idea is it's a sort of a creative way of trying to get around the problem of induction. So what Popper says is from a theory, typically a deductive theory that makes assumptions and then deduces certain consequences from those assumptions, you develop predictions about something. And those predictions become empirical hypotheses that you can test to see if they work. And you determine whether the predictions match the empirical evidence that have been gathered to test those hypotheses. And then now here's the sort of critical trick. You don't actually accept the theory or accept the hypotheses. All you can do in the falsificationist way of thinking is you can either reject them or you can fail to reject them. You can fail to reject a hypothesis or you can reject a hypothesis. If you reject a hypothesis, then you reject the theory. And the logic, the sort of symbolic logic of it goes a little like this. A implies B, right? So A is your theory, B is your prediction, right? So if A is true, then B is true, right? If you find that B is false, then logically you can infer that A must be false, right? Because A implies B. If A were true, then B would be true. If B is false, A cannot be true, right? There's no way that A is true and B is false at the same time. Logically, there is no problem there. As long as I can show B is false, I can infer logically that A must be false. However, if I find that B is true, I can't necessarily infer that A is true. A implies B, but B does not imply A, right? So it's certainly possible. One way of thinking about this, slightly morbid, but if you jump off a building, then you will die, right? You can if you jump off the Empire State Building, then you will die. If I find a dead person, I cannot say, oh, well, obviously they jumped off the Empire State Building because people die of all kinds of different reasons, right? It had nothing to do with that. On the other hand, if I find that you're alive, I can definitely infer that you didn't jump off the Empire State Building, because if you did, you'd be dead, right? That's the sort of intuitive logic of how this works. And it gets around the problem of induction, because the problem with induction is you're trying to make positive evidence support a positive argument, right? Well, I haven't found, there are no black swans, therefore I can infer that no black swans exist. In this case, we're simply rejecting or failing to reject a prediction. So to address the black swan problem in the context of the falsificationist sort of way of thinking, what I would say is my theory is, for some reason, black swans can't exist. And then the hypothesis that gets generated is there are no black swans, right? If I go out and collect a data set in which there are no black swans, I have not confirmed that hypothesis. I have merely failed to reject it. Any one black swan I find will reject the hypothesis and therefore reject the theory. So I can reject theories with evidence, but I can't really accept them. That's the way that you get around the problem of induction here. So does it get around the problem of induction? Well, in a sense, yes. In a sense, because it changes the subject. It asks a different question. And Popper's way of sort of formulating these questions is consistent, meaning the questions that it asks, it can effectively answer. It can falsify or fail to falsify theories. One way of thinking about this is, if you were to apply the falsificationism standard to evidence, the hypotheses that you failed to reject and the theories that produce those hypotheses would tend to be maintained in the scientific literature and presumably would predict events, future events, and explain those events which have already happened. Those theories that produce hypotheses that were falsified would be discarded and replaced with something else. So by that standard, it works. And so the way of thinking about this is, it sort of works on its own terms. It doesn't solve the problem of induction, because it doesn't make it possible to somehow make positive evidence definitively support positive hypotheses or positive theories. It just changes the subject. It asks a different question. So this way of thinking has been very influential in sort of how science, for example, gets taught to high school students, or how science gets even taught to sort of introductory college students in science. A lot of the sort of little sketches or models you see are essentially a version of falsificationism that has been distilled and polished to sort of fit into a nicely communicated block, if that makes sense. So, for example, if you were to go onto the Wikipedia page, if you went onto Wikipedia and looked up scientific method, you would see this diagram right here. And if I expand this diagram, what does it say? Here's how it said. What is the scientific process? You make observations, think of interesting questions, why does that pattern occur, right? Formulate hypotheses, which is basically theory development, develop testable, empirically testable predictions, gather data, and then refine, alter, expand, or reject. Never accept hypotheses. And then sort of that goes in a cycle, and then you develop general theories which ultimately lead to new questions and new hypotheses, right? So theories are ultimately the source of hypotheses and predictions, which then get refined, but never really sort of accepted, right? So this is sort of a distillation of some of Popper's ideas, and the idea is we never prove anything. We just reject or fail to reject things, and if you fail to reject something enough, eventually it becomes accepted as a useful tool that we can use to explain and predict the things that we're interested in explaining and predicting. So now let's apply this general idea to a sort of a simple social science example and see how it works. Okay, so to give you a sense of how the falsificationist way of doing science works, let's take a look at a sort of really basic example. I'm going to propose a theory, okay? A theory of what countries are most likely to win at an Olympic Games. And with the Winter Olympics coming up very soon, maybe this is of heightened interest. So the research question I'm going to ask is, what determines the degree of success that a country enjoys at the Olympic Games? Okay? And the first thing we need, according to our description, is a theory, right? We need a theory of why countries win more or fewer medals than others. So I'm going to start by making a couple of assumptions. I'm not going to test these assumptions directly. I'm just going to make them on the basis of things that I already know, or I think I know at least. And they're going to enable me to make hypotheses that I can then test empirically. So my first assumption is that Olympic champions are the product of rarely occurring genetic mutations, which of course is not to say that Olympic athletes don't prepare a lot. They do. I don't think there's a single Olympic athlete that doesn't train obsessively these days. But if I trained obsessively, it wouldn't matter. I still would probably break my neck on the downhill slalom or whatever. So you have to have certain heightened reflexes, heightened muscle mass, whatever it is. It varies according to the demands of the particular sport you're in. But you basically have to you're born a champion. Of course, you can be born with the characteristics and not do the training, and you never end up being an Olympian. But if you aren't born with those characteristics, you're never going to be a gold medalist, right? You're never going to beat everyone else in the world. So the first assumption is, in order to be an Olympic champion, you have to have certain genetic mutations which make it possible for you to be an Olympic champion. Another assumption is that countries with larger populations will have a larger number of, a number of people, really, with rarely occurring genetic mutations. And this is just the principle of, if something's rare and you draw more samples out of a bigger population, or you draw more samples out of the population, you're going to get more of those rare events, right? So if 1 in 1,000 people, probably it's far fewer than that, but if 1 in 1,000 people has what it takes to be an Olympic champion in some sport, but I only have a country with 50 people in it, I probably don't have any Olympic champions. If I have a country with 1 billion people in it, I probably have quite a few people who have the potential to be Olympic champions. So countries with larger populations will have a larger number of of rarely occurring genetic mutations. And so my deduction or prediction from this is the hypothesis that I'm going to test, is that countries with larger populations will have a larger number of Olympic champions. Now, I am not saying every large country will have more Olympic medal winners than every small country. What I'm saying is, on average, countries with larger populations will have a larger number of champions because they have a larger pool of potential champions to draw from. If, for example, a country didn't have a very good Olympic training program, the fact that they had more people might not matter. And a country might be able to win a few more medals even with a relatively small population by intensively investing and developing in every single person they have that has potential. So it's not going to be the only influence. It's not going to be the sole influence, but it's going to be an important influence, and we should be able to see this in data if we check. So that's what I'm going to do. Translating this into a testable hypothesis. So I have sort of created a little graph here, and I should be able to draw on this. Let's see. This is under content editing. Text highlighting. I know there's a pen around here somewhere. Here we go. No. So we wouldn't expect to see every single dot right on that line, but we would expect to see dots sort of clustered sort of scattered around that line, moving upward together. And I should note, this theory is about, you might have seen log population, right? Not population. The natural logarithm is just a transformation, we discussed it earlier in class, that tends to make really big numbers proportionally closer to small numbers. So you can see the size of the transformation gets bigger. In other words, the degree to which 10 is mapped to 2, 4 is mapped to 1, right? So as the number gets bigger, it's monotonically increasing. It's always, as x gets bigger, the log of x gets bigger, but the derivative, the degree to which it gets bigger, shrinks. The slope goes down, essentially. So for studying population, this is helpful because some countries have a huge population, other countries have a relatively smaller population. This tends to help put all the countries on a sort of similar scale. So what I'm going to do is load in data from the 2008 Summer Olympics, which I have stored in the POLI 395 folder along with olympics.r, a file which is going to enable me to analyze that data. So go ahead and get on your RStudio, open up olympics.r, and we'll get started on sort of testing our hypothesis, right? This is basically a version of our hypothesis. As population gets bigger, or log population gets bigger, the number of metals should go up. We're going to test this using this data in R. So let's do that. All right, so I'm in the RStudio folder, or RStudio environment. I'm going to click on olympics.r to open up that file. I've got this function at the top here, still from the Black Swan demonstration, so I might actually add a little deletion line here to get rid of that. And I'm going to load in the Olympics data set, and you'll notice in this case, I actually have a library foreign command because this is a Stata data set, not a CSV file or an R data file. And so in order to open this, you have to use the foreign library because it's a so-called foreign language, or not foreign language, but a foreign data set from a foreign program, Stata in this case. So olympics.dta is the program. I'm going to read that in and just call it DTA for a data set. You can see this data set has 37 variables in it. If I look at what these are, all kinds of different variables: state name, which is country, which just seems to be a replication of that, population, some stuff about government expenditures, number of metals won, the log number of metals won, log population is in here as well. So what I want to do is just start off by showing you a little picture, or a little table really, of what countries won how many medals. And so what I've done is I'm showing the DTA data set, that's its name, DTA, and I put brackets on here to say I'm going to actually pull out some arguments from this data set. And the way this works is the first argument is the row, right here. The first argument is the row, and I want all the rows, so I just leave that blank. If I wanted only the first 2 rows, I might come in here and say I want C1, 2, and then I would get the first 2 rows. But if I leave it blank, I get all the rows. And now the second argument here tells me I only want 2 columns, specifically the columns that correspond to the variable names country and metals. So if I run this command, what it outputs is basically the entire data set, which you can see has already been sorted with all the countries and all the medals. So the United States won 110 medals in the 2008 Summer Olympics, China won 100, the Russian Federation won 72, and so on. All right, so now what I want to do, going back to my script file here, click here, is I want to look at the relationship between metals and population. And actually, I used to do this by attaching the data set, but that's probably a bad practice. So I'm going to go ahead and just explicitly in every single command say I want to plot, for example, DTA metals versus DTA pop, which is population. And you can see this is kind of a hash. I kind of get, I kind of get nothing out of this. You can't tell what's going on. But if instead I plot metals versus log population, I'm getting a little something more, right? So what I'm getting is the bigger countries do tend to have more metals, but the relationship is far from linear. It actually almost looks curvilinear, right? It's basically there's a sort of critical threshold size of population at which you can earn metals, and then all of a sudden you start earning metals. And from that point on, the relationship seems to be kind of noisy, but basically linear, maybe. But there's a lot of zeros in here. There are a lot of countries that don't earn any metals, and they're sort of bombarding the lower reaches. So maybe I want to just look at the countries that do win some metals. So I'm going to subset the data and only look at those countries that have earned some metals. And so I'm going to say I want to look at now just that subset of the data. This is the subset of the data for which metals have been earned by some countries. So I've just taken out all the zeros, essentially. And what do we see here? Well, it makes it a little clearer to see basically there is something possibly approaching a noisy linear relationship here, although certainly, I wouldn't say it's ironclad. There's certainly a lot of noise in there, but maybe something that's sort of linear. Okay, so going back to the original data set that has all the countries in it, including the ones that earn no metals, that previous graph, I'll just click back here to that previous graph, made us think maybe there's a curvilinear relationship. So instead of fitting a line to it, maybe we want to fit like a parabola. So if I add to the DTA data set a variable that's just the log of population squared, I'm calling that ln pop sq, which is just equal to the log population variable squared. And then DTA, I'm going to run a linear model that basically tells me whether those relationships are in there. I'm going to create I need to DTA. Yep, there we go. Wait. Oh. There we go. So I'm just going to predict fitted values basically for all the different observations in the data set from this model. I'm going to put them in order. I'm going to do a plot of the metals versus the log population. That's just this graph again. And now I'm going to plot that curvilinear. Whoops, I need to put in DTA. That's the line I fitted basically to this data set. I ran a little linear regression with a little curvilinear relationship in it. And what it's telling me is maybe it's the case that that's basically a zero relationship in here and then a bit of a positive relationship in there. If I even want to go further, I can do a model that includes some control variables and so on. And maybe I get it looks like I actually do get a positive relationship between log population and the number of metals won, which is consistent with my hypothesis. Is there something going on here empirically? Well, maybe. We at least see some evidence that you have to be a relatively big country to be able to earn metals. Small countries just have a hard time competing on earning metals. And we can see that even more clearly if I basically rearrange the data set so as to, instead of counting the number of metals, I just classify you as you either got metals or you didn't. So line 26 here creates a new variable called any metals that just is a 1 if you got any metals at all and a 0 if not. And then if I do a plot on whether you got any metals versus your log population, that is a pretty strong indication that you have to have a population of a certain size in order to essentially achieve a certain number of metals. And I can even add in a little linear fit to that. Oh, I'll just do it this way. That ought to work. Yeah. So it looks like there is kind of a positive relationship here. As the log of population goes up, the linear estimated probability of winning at least one medal definitely goes up with it, right? So it looks like, the number of medals, the relationship is kind of noisy. There are lots of other things that are predicting how many medals you win. But you have to have a population of a certain size to essentially be in the running, essentially to have a pool of people available to be your Olympic champions, and then you have to train them and yada yada, and you have to win, right? But you got to have essentially a certain recruitment pool to make that happen. So our hypothesis is, I would say is quote unquote confirmed. We as we mentioned with falsification, we never really confirm hypotheses. We only fail to reject them. Statistically, we found there is a positive relationship between the number of medals and population. You can use that one. If you look at a linear regression of, actually, if we even just do a basic linear regression of and then a summary of that, you'll see there is a positive relationship. Every 1 unit increase in the log of population tends to increase the number of medals you earn by, 2.7. But looking at the data set, that's not exactly a linear relationship. Maybe it's really more of a sort of curvilinear relationship. Maybe it's really more of a necessary condition. Within some kind of broad bounds, our hypothesis was not falsified, although not exactly as cleanly as the way we stated it. We certainly, under no circumstances, have we proved our theory to be true or correct. We have not done that at all. We probably failed to disprove the theory, right? Looking at that evidence, I would say we failed to disprove the theory. But there are lots of other theories that might have predicted that same relationship that we found. So maybe larger countries also have greater tax revenue, which they can then put toward training Olympic athletes more intensely and thus win more medals, right? That same theory might predict a relationship between population and number of medals. So we have to sort of go back to the drawing board there and think, okay, well, if both of those theories can both predict the same prediction, how do we separate them? Well, we need to think of a new prediction, right? A prediction that would only be true for one of them. If you are able to repeat that process over and over again, and a certain theory, for example, my little theory of genetic mutations, if that survives over and over again, then we never really proved the theory, but we at least may come to believe that it's a useful, interesting, explanatory, and even predictive relationship. Now, in the hard sciences, the ideal is much more stringent than that. So going back to our studio relationship here, in the socials or in the hard sciences, finding a relationship like this when you predicted that as log population goes up, the number of medals you earn goes up, that wouldn't be very satisfying. We'd be looking for a law-like relationship, literally a mathematical statement where all the data points were almost exactly on the line, net of a small amount of measurement error. And in social sciences, sometimes we are able to come up with that. So I'll give you a few examples here. Duverger's law says that the number of viable parties in a electoral district is equal to 1 plus the number of seats available in that electoral district. So in the United States, where congressional districts are all separated, so there's 1 congressional seat per district. Every state, there's 1 Senate seat up for election at any given time. You never have 2, or very, very rarely do you have 2 senators both running for offices at the same time. And you actually can't run in both elections, right? You can't run for 2 Senate seats simultaneously. We would predict, Duverger's law would predict in that case, that there will be two viable parties, one plus the number of seats. There's one presidential office available at one time, right? You can't have three presidents that all win the election. And so we should have two viable parties, and we do. In the UK, they also use single-member districts with first-past-the-post electoral rules. Duverger's law also predicts in that case they should have two viable parties, and they have 2.5. The Labour and Conservative parties dominate the process. The Liberal Party has a few seats, and then there are a couple of regional parties that hold some degree of sway. In countries like Germany that use proportional representation systems where the number of seats you get in the legislature is proportional to your vote, there are many seats simultaneously open and all contested, and essentially everyone runs in the same election at the same time, at least for some of the seats in the proportional representation part of the election. And so we should have many viable parties. Many seats are open simultaneously. We should have many viable parties, and they do. Another example of a law-like relationship is the democratic peace. And the democratic peace says no two countries should ever go to war against each other if they are both democracies. Democracies might go to war with non-democracies. Non-democracies might go to war with other non-democracies. But democracies shouldn't go to war with each other. And there's a theoretical framework behind this. But the law-like prediction is two democracies never go to war. Certain cases are disputed about whether they're both really democracies. But in general, it's very hard to find a war between two very clear-cut democratic states. You can find some maybe sort of marginal cases, either very low-level conflicts or conflicts between countries that are marginally democracies. Generally speaking, though, that holds. However, it's much more frequent in social sciences to not see law-like relationships, but to see probabilistic relationships. And let me give you an example of what this looks like. So let's say I'm studying the relationship between voting patterns and income, okay? Personal income, the amount of money I make. A law-like relationship might say income is related to the probability that you vote Republican, and one type of law-like relationship is, well, if you're poor, which I defined here arbitrarily as less than $50,000 a year in income, you never vote Republican, and if you're rich, you always vote Republican. Obviously, nothing even close to that exists in social scientific data. I don't think anything separates out voters quite that much for a variety of different reasons. So it's extremely unlikely for us to see this. Also, somewhat unlikely, but at least more plausible, is that your income is associated with your probability of voting Republican. So people who make $20,000 a year, I should emphasize again, this is simulated. This is a simulated process, not real at all, not based on any real data. Somebody who makes $20,000 a year has like a 5 or maybe 10% chance of voting Republican. Somebody who makes $50,000 a year, it's a coin flip, half and half. You know, those who make $100,000 a year or more are almost all voting Republican. That means that if I find a person making, let's say, $30,000 a year, there's a 10, 15% chance they might vote Republican. I will find some individuals voting Republican in that case. It's not a individually law-like relationship. There's a probabilistic relationship going on there. But at the group level, it's law-like. All people making $30,000, they all have a 20 or 15% chance or 10% chance of voting Republican. So at the group, it's law-like. Individually, it's probabilistic. Maybe a little more realistic for human behavior given the complexity of what goes on when people make decisions. Even more realistically is something like this. Both individuals and groups exhibit probabilistic behaviors which are systematic but not deterministic. So for example, every point in this graph is a person. You can see the people making $50,000 here have a spread of different probabilities of voting Republican. Some have a relatively low probability of voting Republican. Some have a relatively high probability of voting Republican. If I were to average over all these people who make $50,000, on average they have about one half probability of voting Republican. If I could measure somehow individuals' probability of voting Republican, and then plot them against income, I might see something like this, and I could easily look at this and say, yeah, there's definitely a relationship here. I could probably fit an S-shaped curve to this relationship. In fact, it would look like that, probably. But that doesn't mean I'm going to be able to predict any individual's probability of voting precisely. So on average, I can say people who make $50,000 a year have about a half probability of voting Republican. Some people will have a lot more, some people will have a lot less, and that's going to depend on a variety of things, including probably things about them I didn't measure, and a pure random noise component. Relationships in the hard sciences, might look like this or this more often, because they are typically examining phenomena that are under careful laboratory control with no outside influences influencing sort of the what happens, right? The dependent variable that they're studying, PR Republican in this case. In our example, people's voting decisions are influenced by innumerable things, not just their income, and we don't have a laboratory where we can hold people's personal characteristics constant. So the data look more like this. And therefore, when we assess relationships, we tend to see noisier relationships. Going back to our Olympics example, relationships that look more like this, right? That look sort of like a pattern, but certainly not a deterministic pattern. Or even, our looking at whether countries earn any medals at all, that was a little cleaner, but still not what I would call perfectly razor sharp, right? Plenty of noise going on in there. The reason for that is because we don't have the benefit of experimental control. We cannot basically rule out all other influences on an object or on an object of study. So when we're studying voting behavior, we have to study votes by people who don't live in labs. And consequently, probabilistic relationships are closer to what we usually find. And we have some theoretical reasons to believe that it's not just a matter of, we can't find deterministic relationships even though they're there. It may be the case that deterministic relationships don't even exist because there's a random component to human behavior that cannot sort of be reduced, right? We can't get that down to a point. So for those reasons, we're more likely to see data that look like this. All right, so that's it for this lecture. I'm going to leave you with a little question here. So at the very beginning of this lecture, we had a little talk from Richard Feynman, who was saying that social sciences aren't real sciences. They don't exercise the kind of care and checks necessary. They don't go through a scientific procedure that is really designed to uncover truths about the empirical world, truths about the social world. And right now, I think it's fair to say, in your third lecture of a research design class, I don't think we know enough yet in the class to be able to make an informed decision about whether he was correct. But I want you to keep that question in mind as you move through the semester. Be thinking about, what does it really take to be able to draw a firm inference, a scientific inference about people's behavior, and be asking yourself, for every article you read, are they really taking an approach that would enable us, given all the problems that we're going to study in this class about social research and scientific research in general, are they really taking the approach that would be necessary to enable them to really answer a question with a reasonable definitiveness? So be thinking about that, be having that question in your mind as we move through the semester, talk about research design and statistical inference. And then we will, not next week, certainly not next class, we'll come back to it, right? We will revisit at the end whether he has a point and whether he's being unfair to social sciences or whether we actually are taking the care necessary, or maybe something in between. All right, so I will see you in the next class.